Hi everyone. So today we are going to start a new module which is bidirectional pure bending of beams with arbitrary cross section. So we are done with the lecture or the module on torsion of thin wall structure. So we move into the next chapter of the course, which is the bending or bidirectional bending of beams with thin wall cross section, like an I-beam, a beam with a C-section, a box beam with a thin wall, a box beam with thin wall, and other such cross sections. But however, in this lecture, we will talk about generic bidirectional bending of any arbitrary cross section, and in the later part, we will move into bidirectional bending of thin wall cross section. So before I go into the bidirectional bending, let me give a brief recap of the unidirectional bending of beam that you have studied in your previous courses, both in the course on mechanics in the first year as well as the first course on aerospace structure that you have done last year. So the knowledge of unidirectional bending of beam is a prerequisite to what we are going to talk in this lecture. So therefore I thought we should start with a brief recap of unidirectional bending. So let me start with a brief recap of unidirectional bending. Okay, so let us consider the beam that I have drawn here. So x and y axis are the in-plane or the cross-sectional plane axis, whereas z axis is the axis parallel to the length of the beam. I have taken a rectangular cross section just for the ease of drawing, but the theory that I am going to talk about, okay, the theory of unidirectional bending, as you might appreciate, applies to any arbitrary cross section and need not be a rectangular cross section. And another point that I wish to highlight is that we are talking about pure bending. What is meant by pure bending? Pure bending is when the only external force that is acting on the beam is a moment. Okay, there is no other force or moment acting on the beam. There is no axial load, there is no shear force, there is no torsional moment. So the only force that is acting is bending. So in unidirectional bending, only one bending moment acts on the beam. So in this case, let us take that as mx. Okay, so mx is the moment acting on the cross section of the beam or on the beam, so as to say, about x axis. So this is mx, and let me say that this is nothing but the cross section of the above beam. Okay, so you also might be aware that the unidirectional bending of beam that we had studied earlier is based on Euler-Bernoulli beam theory. Okay, so Euler-Bernoulli beam theory is the most elementary beam theory and is also sometimes called as the engineering beam theory. Now, Euler-Bernoulli beam theory has certain assumptions and we should be well acquainted with those assumptions before we move into bidirectional bending. So, the first assumption is that the plane cross section remains plane after bending. The plane cross section remains plane after bending. Okay, that is the there is so the cross section that is plane before bending, the rectangular cross section in this case, is going to remain plane even after bending. That is the first assumption, and the second assumption is that the plane remains perpendicular to the neutral axis even after bending. Perpendicular to the neutral axis after bending. Okay, so it is very important to understand these two assumptions of Euler-Bernoulli beam theory. If you have forgotten, it would be a good thing that if you revisit these two assumptions and understand what these two assumptions are, because though we will be talking about bidirectional bending, but the bidirectional bending will also be based on Euler-Bernoulli beam theory. Okay, so now the next point that we should understand about unidirectional bending is that the under pure bending, the only stress that is produced in the cross section of the beam is normal stress or direct stress. Okay, that is sigma z. So sigma z is the only stress that will be produced in the cross section due to pure bending. So pure bending is going to produce only direct stress, only direct or normal stress. That is another important point. Okay, so that is another important point that you should recap before we move into bidirectional bending. Okay, so with this recap, we will move into the topic of today's lecture, that is bidirectional bending. So let me clear the canvas. So let me first draw an arbitrary cross section. Let me draw the in-plane axis, that is x and y. Okay, and the axis passes through C, which is the centroid of the cross section. Okay, so I have just drawn the arbitrary cross section of the beam. I have not drawn the entire beam. I have just drawn the cross section, which can be arbitrary. Okay, so this is the cross section of the beam. Beam under biaxial bending, bidirectional, sorry. We also call it biaxial. Okay, now, okay, so now the two moments, so since it is bidirectional, the bending moment will be applied about both the axes. So let us draw the bending moment. So one is mx and other is my. So mx and my are the applied moment or external moment, right, or external moment about x and y axis respectively. Okay, so now if let us first, before we move into the theory, let us first talk about the sign convention. Okay, so bending moment that produces tensile stress, okay, in the first quadrant is considered to be positive. Okay, let me write it down. Bending moments producing tensile stress or tension, tensile stress or tension in the first quadrant of the cross section, in the first quadrant of the cross section is considered to be positive as per our sign convention. Okay, so let me just try to explain this. So this is the first quadrant. The moments that produce tension in the first quadrant is taken as positive. Okay, so let us see the mx force. Just try to visualize the mx moment is going to produce tension in the first quadrant, so mx is positive. Similarly, my is also going to produce tension in the first quadrant, so my is also positive. So both mx and my are positive. Therefore, mx and my both are positive according to our sign convention. Okay. Now, let us consider. So let me. Now let us consider a small elemental area and do our further analysis. So let me just erase the canvas and draw a fresh picture. So I just want to keep the cross section clean, so I have to draw a lot of things there. So now, see, in the case of unidirectional bending, we have presumed that the neutral axis passes through the centroid of the cross section. Okay, but however, for bidirectional bending of an arbitrary cross section, we cannot make the assumption beforehand. Okay, so let us first consider that the neutral axis need not pass through the centroid. So let me just draw an arbitrary neutral axis, a possible neutral axis, and we will not make it pass through the centroid. It need not pass through the centroid. So this is my neutral axis. So the neutral so now what I do is I take a small elemental area dA. So this is dA, which is an elemental area. Okay, now this elemental area, the perpendicular distance of the elemental area from the neutral axis, let us call this zeta. Okay, and of course it is making a distance, it is at a distance x from the y axis and y from the x axis. Okay, so zeta is the perpendicular of the neutral axis, perpendicular distance of the elemental area dA from the neutral axis. Okay, now the normal stress produced in the elemental area sigma z can actually be written as, so sigma z normal stress, normal or direct stress, whichever you are more comfortable with. So the normal or direct stress in dA at dA is sigma z. Okay, so just to repeat, since this is a problem of pure bending, the only stress that is going to be produced in the cross section is the normal stress or direct stress sigma z, and sigma z can be written as E into epsilon z, where E is the Young's modulus and epsilon z is the normal strain. So this can further be written as E into zeta by r, where r is the radius of curvature of the beam. Okay, now so this is for sigma z at dA. Okay, at the elemental area dA. Now let us try to understand this expression. So if you go back to your unidirectional bending, you will remember that the normal stress in the at any point in the cross section was equal to Young's modulus into y by r, where r was the radius of curvature and y was the perpendicular distance along the y axis from the neutral axis. Okay, exactly the same concept is applied here. Zeta is the perpendicular distance of the elemental area dA from the neutral axis. Therefore, the normal stress at dA can be written as Young's modulus into zeta by r, where zeta by r is the normal strain at dA. Now, if this is the expression for sigma z, then, and r is of course the radius of curvature, then we can write the beam, we can say, since the beam is under pure bending, the resultant normal force, the resultant of normal force on the cross section, is 0, as this is the case of pure bending. Right? There is no externally applied direct force, axial force or shear force. So the result, so there is no applied axial load. Therefore, the resultant of the normal internal normal force should be equal to 0. And how is that represented? The resultant of the normal force is nothing but dz, sigma z into dA integrated over the total area. And so this is equal to 0. Right? So if this is equal to 0, I can write this as E by R area integral of zeta into dA is equal to 0. Okay, right? So now what is this zeta into dA? Area integral of zeta into dA. So this is nothing but the first area moment. Okay, now try to understand. The first area moment about the neutral axis, the first moment of area about the neutral axis is equal to 0. Okay, since the resultant normal force is going to, on the cross section is 0, that gives us that the first area moment of the cross section about the neutral axis, that is the green line, is equal to 0. So if the first area moment about a certain axis is equal to 0, then the axis should pass through the centroid of the cross section. Right? Only if an axis passes through the centroid of the cross section, the first area moment about that axis is going to be 0. So therefore, this implies that the neutral axis should pass through the centroid of the cross section. Okay, therefore we can say that if even for bidirectional bending of any arbitrary cross section, the neutral axis passes through the centroid of the cross section. Okay, right? So this is the final takeaway that we get from the entire analysis. So the neutral axis of a arbitrary cross section under bidirectional bending is always going to pass through the centroid. Okay. So in the next lecture, we will try to find out the expression of the normal stress sigma z in terms of the applied moment mx and my.